Our topic of the day is the area of regular polygons. To do this, to cover the notes we're doing today, we are going to be using the area of regular polygons flipbook. Mine is white, but yours should be purple or some other color. And then we'll also be using this discovery activity on area of a regular polygon. So take a couple minutes to get those out, and then we'll get started. Okay. While you're getting those out, let's review a couple terms real quick here. So we've got this word regular. What does it mean for a polygon to be regular? Feel free to shout it out or send a message in the chat. Okay, so I'm seeing original in the chat. I like that. That's an interesting thought. What do we know about the sides of a regular polygon? What can we say about the sides? And what can we say about the angles? Yeah, exactly. So in a regular polygon, all our sides are congruent. And all our angles are congruent. So I'm going to move our discovery activity out of the way. We'll come back to that later. But for now, let's just talk about our little flipbook here. So if you can all open up on the inside front page, we have this diagram. And then we have four terms that we want to cover today. So before we get super far, I want to introduce these terms just so that we all have a common ground going forward. Our first one is the center of the polygon. The center of the polygon is the point that is equidistant from all of the vertices. From all of the polygon's vertices, should be more specific there. What does the word equidistant mean? What does that word mean?
The equal distance?
Yeah, exactly. We can just break it apart. Equidistant means that it's the same distance away. So now let's look at our polygon and let's see which point we can say is the center. Are there any guesses which point would be the center of our polygon here?
S?
S. Perfect. Yeah. S is our center. All right, let's look at the next one. Radius of the polygon. This is the segment from the center of the polygon to any vertex. Okay. So radius, think about that word radius. What other type of shape has a radius in it? Shout it out or send it in the chat.
Circle.
Awesome, yeah. Circles also have radii, or radiuses, however you want to say it. And what we know about the radii is that they're the same length. So can I get someone to let me know, or to identify one of our radii in this polygon?
SQ.
SQ, perfect, thank you. So we've got SQ as one. And then do we have another radius?
ST.
ST. Okay, that's an interesting choice. We're actually going to talk about that segment later. That one doesn't go to a vertex, it goes to a side. Do we have any other? One more time?
SR.
SR. Awesome. Okay, so we know that SQ and SR are radii. We also know that since S is the center, these two distances are exactly the same. We can mark these lines congruent. What type of triangle do we have here? If we have one pair of congruent sides, what's the special name we have for that triangle?
Is it right angle?
Right angle. Okay, so if we look at one of these smaller ones, we do have a right angle. That's true. But if we're looking at triangle SQR, so my hint, yeah, very nice, very nice. Isosceles. Saw that one in the chat. Triangle SQR is isosceles. Okay. Our next word's kind of a funny one. This is one that we probably haven't worked with before. Today we're talking, one of them is apotheme. So the apotheme is the height of the isosceles triangle formed by two consecutive radii of the polygon. So if we look at our triangle formed by SQ and SR, what segment do we think gives us the height? Get our triangle here. We want to know how tall our triangle is. And when we think height, I want you to think yeah, very nice. So when we think height, I want us to think right angle. So we only have a right angle here, right? So this means that ST is our apotheme. So We're going to get a lot more practice working with these apophthegms in the future, but I just want to make sure that you get this definition down. Our last term is the central angle of a polygon. The central angle is the angle formed by two consecutive radii. So the way we can find our central angle is we look and we say, okay, I've got one radius here, one radius here. Are they right next to each other? Are they consecutive? Do they go to the vertices that are consecutive? Yes, they do. So we can say our central angle is equal to angle QSR or angle RSQ. The order doesn't particularly matter. We just want to make sure that we know that this is, in fact, the central angle. So, all right. Now that we've got our new definitions down, let's start practicing with some of these. So if I can have you turn in your flip book to the next page. We're given this problem, and we're all dealing with angle measures. In our diagram, A, B, C, D, E, F, G, H is a regular octagon. How many sides does an octagon have? Awesome. Yeah, thank you. Octagon means we have 8 sides. We want to find each angle measure below. Okay, our first angle that we're looking at is angle EZD. Well, that's this one right here. Any ideas how we could find angle EZD? My hint to you is that we know EZD is a central angle. If we look, we've got one of our radiuses, EZ, and another one, DZ. Luckily for us, we have a formula for central angle measure. So I would write this down. Our central angle is equal to 360 divided by the number of sides. So all we have to do is say angle EZD is equal to 360 divided by 8. Which means that angle EZD is equal to 45 degrees. Okay, cool. So we found angle EZD. Now let's look at angle DZX. Angle DZX is this angle right in here. Do we have any guesses about how we could try and find DZX? Any ideas of things we could do? Awesome, exactly. We noticed that angle DZX is equal to 1/2 angle EZD. So what that tells us is that DZX is equal to 1/2 of 45. Yeah, and then all we have to do is we can say this is equal to 45 over 2, which is equal to 22.5 degrees. Okay. So we've got one more angle that we need to find the measure of. Angle XDZ. What ideas do we have on how we could solve for angle XDZ? That's our angle right in here. One of the answers I'm seeing in the chat is, wouldn't it be the same as the second? And while that's a good thought, we don't necessarily have enough information to say if these two angles are congruent. What do we know though? We've got a triangle here, right? What do we know about the interior angles of a triangle? What do they measure? What do they add up to? Exactly. 185 degrees. So let's say that we have 100. We know that the interior angles equal 180. If we look at our triangle, we know we have 90 degrees here. We can say 90 degrees plus, we have 22.5 degrees here, plus 22.5, plus our mystery angle, x, which would be this one, equals 180. This means that 110.5 plus x equals 180, which means that x is equal to, 112.5. I apologize. 112. This is why we do math in pencil. That we get 112, and I'm just going to cross this out and write it nicer. 112.5 plus x equals 180, which means x is equal to 67.5 degrees. Okay. That's all we have to do for some of these angles. The two that I would pay the most amount of attention to, problem number 1 and problem number 2. You're going to be doing those a lot in future examples. Okay. Now, we're going to put the flip book away for a second. And if I can have you get out your discovery activity on regular polygons. This is going to be on page 265 in your math notebook. So I'll give you a couple seconds to do that. Okay. So now that we have these regular polygons, we want to know how to calculate their areas. So we want a formula for that, right? Formulas are fun, formulas are easy, and we can just plug stuff in. So let's try and find one. Consider a regular polygon with side length s. So each one of our sides is s units long, divided into congruent isosceles triangles. So that would be a triangle like this one we have here. Each triangle has a base length of s and a height of a. I'm going to box those up because we'll come back to those. The distance a, or our height, in a regular polygon is the perpendicular segment from the center of the polygon circumscribed circle to a side. And this is called the apothem. Our next blank asks, the area of a triangle in terms of A and S is what? So the first question I have for you all, what is our area formula for a triangle? Feel free to shout it out or send it in the chat. Yeah, awesome. So the area formula we're looking for is area equals 1/2 base times height. Okay. So looking at our problem statement, what variable did we assign to our base? Look in these first two paragraphs here. If we look through our statements, we see that we said that the triangle had a base of S and a height of A. So what we can do is we can take those variables and we can plug them into our formula, which means A equals 1/2 S times A. So every triangle that we divide our polygon into, all of these are going to have the formula 1/2 S times A. Now, let's start looking at this table here. Let's say we have a 5-sided polygon. How many triangles can we divide our polygon into? Feel free to shout it out or message it in the chat. 5. Awesome. Perfect. So we know that all 5 of these triangles are congruent, so they have the same area. And we said that area was 1/2 S times A. This is 5 times 1/2 S times A. Okay. Let's try it again. If we have 6 sides, how many inner triangles do we get? 6. Perfect. Which means that our area is 6 times 1/2 S times A. We can continue filling out this table, for our 7 through 9 values. Now, let's generalize it. If we have n sides in our triangle, so some mystery number n, how many inner triangles do you think we will have? So I see a lot. I see 2n in there. And 2n's pretty close. So remember, if we had 5 sides, 5 triangles, 7 sides, 7 triangles, so on and so forth. So if we have n sides, n triangles, which means that our formula is n times 1/2 S times A. Okay. The next question asks us what the perimeter of a regular polygon is. What does perimeter mean? What is a perimeter? Shout it out or send it in the chat. Perimeter is our distance around the figure. And the way we get that is we take all of our sides and we just add them together. So if we have a regular polygon with side length of S, all of our sides are going to have that length S. So we can say that P, our perimeter, is equal to S plus S plus S plus dot 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 plus S. So now we're going to assume we have n sides. So if we have n sides, we have to add S to itself n times. This means that our perimeter is equal to n times S. We've got one more box to fill in down at the bottom. And that what this box does is it sums up all of our conclusions. So the first question is, or the first blank, the area of a regular polygon is A equals, and then we're going to take this formula we have here, and we're going to rearrange it a little. So A equals 1/2 A times N times S. And this is in terms of N and S. Now, my question to you, does this NS, does that look like anything else on our page? Feel free to shout it out or message it in the chat. Yeah, very nice. So this NS is the same thing as our perimeter. So for our next formula, in terms of perimeter, we say that A is equal to 1/2 A, and then instead of NS, we're going to replace that with a capital P for perimeter. So remember, big A is the area, big P is the perimeter, our little a is the apothem, S is the side length, and N is the number of sides. This is the discovery activity that you will turn in on Canvas in the 11.3 Discover activity slot. So if you want to take a quick picture of this or screenshot or of whatever you have and turn that in, take a couple seconds to do so. We are now going to move back to our normal flip book, and we're going to finish it out with a couple example problems. So take a couple seconds to get your stuff turned in, and then we're going to be right back in here. Oh, yes, I see a question for the bottom of the discovery page. There we go. And again, this is what we are going to turn in the 11.3 discovery activity. It should be in your modules for this week. Okay. Let's go back to our foldable and let's finish this bad boy out. If I can get you to open to our last page, up at the top, we have a spot to write our formula. So let's just copy these formulas down again. We're going to say A equals 1/2 apothem times the number of sides times the side length, or A equals 1/2 times the apothem times the perimeter, where little a is apothem and P is perimeter. Okay, let's do some examples of these. So our first one, we find the area of each polygon below. Looking at number 4, the first thing I like to do when I'm doing a problem like this is I like to write out what I know and don't know. So I'm going to write out the variables in our formula, our apothem, the number of sides, and the side length. Which of these variables can we fill in? A. Yeah, very nice. We can fill in A. So if we look at our diagram, we notice we have our apothem right here, 6.5, right by our right angle. So we've got our 6.5 there. What else can we fill in?
S.
S. What would S be? Interesting. So what we've got to remember, this 8, that corresponds to this piece right here, or to this piece. 8 isn't a side length, but it's our radii of the polygon. S would be this length down here. We don't know that one. Do we know how many sides we have? 5, exactly. So we can fill in n equals 5. Okay. So if we look at our problem, we got A, we got N, but we do not have S. Are there any ideas how we could solve for S? What could we try doing? What I would think is I notice, we've got a right triangle here, and we know 2 of the sides. What if we used our Pythagorean converse to solve for the other side? Our converse is c squared minus a squared equals b squared. So I see, yeah, so I see a couple ideas in here, and I see a couple in the chat. I'm sorry, I should have noticed this sooner. But if we use the second equation, we still need, that doesn't really help us a ton, because we would need another variable for that to work. And the other thing I'm seeing is 360 over 5. That would give us a central angle, and we'll actually use that a fair bit in later problems. But right now, we're just going to use this converse. So our hypotenuse is C, and the hypotenuse of our triangle is 8. So we can say 8 squared minus 6.5 squared equals b squared, which means 64 minus, I want to say it's, this is when a calculator would be helpful, 42.25, thank you, minus 42.25 equals b squared. So 21.75 equals b squared. The last step we need to do is square root both sides. The good news on a problem like this is that we do not need to simplify our radical. We can just plug it into the calculator and take the approximation. So when I plug in the square root of 21.75. It spits out 4.66, and we're going to go 4. B is approximately, since we rounded, 4.664. Now, is this our whole side length, or is it just a fraction of it?
A fraction of it.
A fraction of it, that's right. We only found this piece. So I know that's written really small in there, but we only found this piece. So to get our side length, we take 2 times whatever we have, 4.664, which is equal to 9.328. So now that we have all of our side lengths, we can finally plug it into our equation. We can say A equals 1/2 times 6.5 times 5 times 9.328. We plug that all into our calculator. And I get 151.58 units squared. Let's try another one. Let's look at number 5 next. So again, we can start by writing out what we know and what we don't know. So let's make a spot for our apothem, our number of sides, and our side length. How long, do we know any of these variables?
No.
No. Oh, we know one. We know one. We can always find the number of sides just by counting. If we look, we have 1, 2, 3, 4, 5, 6 sides. So let's draw an apothem on there. Okay. I'm looking at this problem and I would think, I don't really know anything super helpful for us with side lengths. All I have is this 8. So what if I tried to get an angle to go with it? Let's find our central angle. So let's find the central angle. So we take our central angle equals 360 degrees divided by the number of sides, which is 6, which means we get a central angle of 60 degrees. So this whole thing's 60 degrees, but we generally only want half of it. We want that second piece right in there. So what we're going to do is our nice piece is we're going to take this 60, we're going to divide it by 2, and we get 30 degrees. So this angle here is 30 degrees. Now, the smaller my writing gets, the harder it is to read. So I like to redraw triangles when possible. So we've got our triangle with a 30-degree angle here and an 8-unit long hypotenuse. Got our apothem down here. I'm going to say this is x. Okay. Now, I'd look at this triangle and think, God, we have to solve for a ton. But then I would look and see, ooh, we have a 30 degrees, which means that this must be 60 degrees, making this a 30, 60, 90 triangle. We have some really nice equations that we learned for that back in chapter 9. If we remember, our hypotenuse is equal to 2n. Our short leg is equal to n. And our our long leg is equal to n radical 3. So let's look at this 8 equals 2n. This means that 8 over 2 is equal to n, which means that 4 equals n. So we can cross off this piece and make it a 4. Since a is equal to n radical 3, and we know n is 4, then we know a is equal to 4 radical 3. And that makes us happy, and we can plug that in right here. The last thing we need to know is that we need to find our side still. And so we know that this piece is 4 units. So our whole piece must be 8 units, 2 times our small one. For our next step, we've got all of our variables. We've got a, we got n, and we got s. So let's plug them into our calculator. A equals 1/2 times 4 radical 3 times 6 times 8. Plug that into your calculator. 4 radical 3 times 6 times 8. Ooh, not 5. Times 6 times 8. And then divide it all by 2. And it'll spit out 166.28. Approximately 166.28 units squared. Okay. We've got one more example problem for today, and then you're all done. So let's look at number 6 here. Again, let's start by writing what we know and what we don't know. Which ones of these variables can we fill in? Are there any that we know for sure? Shout them out or send them in the chat.
N.
N, okay. How many sides does our polygon have?
10.
Okay, let's see, let's count that just to be sure. We got 1, 2, 3.
It's 12.
12, yeah. I think that's what I counted as well. That's okay though. 12 sides, that's not a huge problem. And do we know any other variables?
S.
Side.
Yeah, we know S is equal to 5. Awesome, thank you everyone. Okay, so the only thing that's missing is our apothem. If we can find that, then we can solve our problem. The way I would recommend starting is let's find a central angle. Let's always do, my general hint is if you don't know where to start, find a central angle. It's a good way to go. We take our central angle equal to 360 over 12, which is equal to 30 degrees. Again, if we look at this last one, we didn't just use our 60. We had to divide it by 2 again. So let's do that one more time. You divide by 2, you get 15 degrees. That's looking better. Give me just a second here. My hint to you, and I have a question in the chat that I need to answer real quick. So now that we have our angle measure, let's redraw a triangle with that angle measure and filling in sides. So take a second to do that on your own and fill in whatever sides we have left. We can while I answer this question. Okay, and we're back. So we look at our triangle, we notice we have our apothem on this bottom here. And then do we know how long this side is? Yes or no?
Yes.
Yes, we do. Yeah. So all we have to do to get this side is take our 5 and divide it by 2 to get 2.5. Okay. Now we need to solve for our apothem. Any ideas on how we could do that? Okay, so I'm seeing 2.5 over 15. So that's interesting, but we have to remember this 15 is an angle and 2.5 is a side. So what I'd be thinking is if we have an angle and a side, let's use trig. So we're going to use our tangent ratio. We're going to say tangent of 15 equals 2.5 over a. A lot of the time on these problems, you're going to have to calculate a central angle and then use that with some trig to finish it. So we know a tangent 15, multiplying both sides by a times tangent 15 equals 2.5, which means a is equal to 2.5 over tangent of 15, which means a is approximately, and again, since we're rounding, we use approximate, 0.5 divided by tangent 15. A is about 9.330. So we can go back up here, fill that in. And the last thing we do is we plug it all into our equation. 1/2 of 9.330 times 12 times 5. Plug that all in. Excuse me. We get A is approximately 279.9 units squared. So, again, the general format for something like this is to write out what variables you know and don't know at the top. Excuse me. You'll always be able to find at least your n. Then what you do is you use your n and whatever little information you have to solve for the other variables. Generally, a really good place to start is using our trig ratios. If you're not sure what to do, use trig. And then the last step, once we found all of our variables, we plug it into the equation and call it a day. So that is the end of day 1 of area of regular polygons.